Welcome, everybody. Avi, there's one thing we could have mentioned. We have a bunch of other custom courses. We include a course like a full day course or half day course for executives. If you have a boss who works in, who reviews your work and doesn't understand machine learning or the basics, the fundamentals, we have courses to assist executives. Howdy to everybody. Leonardo, glad to see you made it in. I saw on Twitter you mentioned you were having an issue with registering, so I guess it worked out for you. Avi, I think there's an error or something there with Mohammed or something. If you want to have a little look at that, I'm not sure what's going on. Yeah. I'm going to go ahead and share my screen and get started with the content for today. Can everybody see my screen? Avi, do you see it?
Yes, I can see your screen, Michael.
Awesome. Thank you very much. I appreciate that. All right. If anybody has any questions, anything you want to chat with me, you want to communicate, jump in. If I ask a question, you want to jump in, you get full credit for anything you say for helping out in the course. I'll be watching the chat window, okay? And Avi will be helping curate if there's any other kind of bigger questions. Let's talk about clustering for inferential machine learning. Just a really quick introduction. I looked at the list and I think I recognize most people. But if you don't know me, my name is pronounced Pyrcz. That's the way we pronounce it after 100 years in Canada. I've been told by my Ukrainian friends that we don't pronounce it correctly, but that's the Canadian pronunciation, I guess. I'm from industry. I did just start as a professor recently, but I do have a lot of experience of everything I teach, I've done in industry. I've used it practically, so I'm driven by practice. I'm flexible if you have other ideas, if you have other content you want to hear about. Actually, Masha had a idea about, hey, we need to see more on pipelines. I'm working on some pipeline content right now to basically be able to abstract machine learning. Great idea. I'm working on that right now. I'm working on a wide variety of different ideas as people suggest things. I have an open door policy. People drop me a line all the time. Share with me the cool stuff you're doing with what you're learning. That gets me excited. I'm stoked to hear that. I'm an engineer and a geoscientist. If I'm speaking to engineers and you are having difficulty understanding, let me know and I will switch. Federico, you asked for the original pronunciation of Pyrcz. You have to find yourself somebody who's, speaks Ukrainian better than I do. Of course, I don't. Or Polish and so forth. I met a variety of people who know how to pronounce it better than I do. Funny, we don't know, right? I am frequently consulting and working in industry. I spent a bunch of time last week working with companies, this morning at a company, 44 engagements, 1,700 working professionals taught last year alone. I do a lot in companies, and I do a lot to also just in general support working professionals. People may have seen my YouTube channel. I do have a lot of content that I share with people to assist in the digital transformation. Okay, I'm happy to help. Let's talk about the goals for today. We're going to talk about clustering for the purpose of inference and really kind of introduce it as a powerful form of machine learning. A lot of people know the basics of clustering. A lot of people worked with k-means. That's where we start. And then we will build upon that to more complicated methods. And I'll even refer to other content where you can continue on your journey. There's lots you can do in inferential machine learning with cluster analysis. The general idea is with inference is to learn complicated patterns from complicated data, high dimensional data. In this case, we're going to try to separate into groups. Okay, let's get into prerequisites. Let's get into details. I said machine learning. Let's define machine learning very quickly so we're all together. I love this. I got in an argument. No, I didn't get in an argument. I got into a discussion with someone about machine learning, what is and what it isn't. If we agree on the definition, I think then we're comfortable to move forward. Study of algorithms and mathematical models. You notice that's plural. It means it's a toolkit of multiple methods. Computer systems use to progressively improve their performance on a specific task. They're learning, they're improving the performance. Machine learning algorithms build a mathematical model of sample data known as training data. Toolkit, learning on training data in order to make predictions or decisions without being explicitly programmed for that task. General, they can be generalized to a variety of different problems. You can train a machine to solve prediction of a seismic attribute or maybe a reservoir petrophysical property from a seismic attribute. You can use the same model to try to make a prediction of, retrained to make a prediction of sand or shale elsewhere or something like that. They should be general. And now what's very interesting is most people, when they read this definition on Wikipedia, they don't read to the end of the article where it says, where it is infeasible to develop an algorithm of specific instructions for performing the task. In other words, if you understand the engineering and the geoscience and you can solve the problem using fundamentals, do that. Don't use machine learning as a crutch. There's tons of good applications, and we could talk a lot more about when we should use data-driven machine learning and when we shouldn't. Now, let me explain a basic concept here. When you see the slide, you're going to be like, what did I sign up for? I didn't think we were going to be covering this type of basic statistics, but this is important. Please bear with me for 2 or 3 slides. The population, it's an exhaustive finite list of property of interest, the features of interest over the area or volume of the study. Generally, the entire population is not known. If it was, I don't think any of us data-driven people would have anything to do. We would know the truth. There'd be no reason to do all the modeling we do. It's the exhaustive set of porosity at all the locations within the reservoir with sufficient scale to make the decision, i.e. to know the volume in place and to decide where to drill the well, or mining grades, know where to dig to develop the mine. The sample is a set of values, locations that have been measured. It's a limited subset. Okay, let's look at this. We got a reservoir, the population. We got the well with the well log with its scale of measurement along the well bore. That's a sample. Okay, so far this is 101. I know everybody knows this. We're together. Let's go one more step. Parameters are a summary measure of the population. Okay, so the mean porosity or average, arithmetic average porosity over the entire reservoir is a population parameter. Now, yeah, it turns out model parameters are a different thing in machine learning, and we're not going to get into those details today, but that is a different thing. It has to do with fit, but there is a relationship between them. We won't go into those details. Statistics, a summary measure of the sample. You got the mean of the reservoir, that's a population parameter. You got the mean of the well, that's a sample statistic. Not a big deal. So we know the statistic, we don't know the parameter. Let's be clear about that. We have the sample, we don't have the population. I hope we're together on that. Now let's talk about machine learning, nuts and bolts. Well, every time I say machine learning, or anybody does from now on, I hope this equation pops up in your head. Ta-da! This idea of y equals f of x is, or x, plus some error term, epsilon. Now, we will term these inputs as being the predictor features, the inputs to the model, and the F is the model that transfers or converts us from inputs to an output. Okay, so that's the response feature is the Y. Predictor features or feature are the inputs. Now, machine learning is all about estimating this model, understanding these types of relationships for 2 purposes, inference and prediction. I hope you can see this is where we're getting back to regular broadcasting at this point. Let's talk about inference. What is the relationship between each of the predictor features? What is the form of the natural setting? The shape of the relationships. There might be relationships that depend on other values, interactions, heteroscedasticity, my favorite word. I've set a personal goal to use it every day. And I just did today. I get full points. Now, if you're trying to understand what exactly inference is, let me give you the world's simplest example. It's given a sample, describe the population. That's inferential. In other words, I take this coin, I flip it 10 times, I get 3 heads, 7 tails, and I ask you, is this a fair coin? Or being the good statistician I am or try to be, I say, what's the probability it's a fair coin? That is an inferential problem. Okay, so we're doing inferential machine learning today. We're learning about the population. We're learning about the system. Why would we do that? Well, we're going to take our well data. We're going to try to describe the reservoir. That's inferential. The reason we do it is because we do it mostly to support prediction at the end of the day to add value. And prediction is all about getting the most accurate estimate of F, an estimate of the natural setting, F hat, in order to go from inputs, predictor features, to response features, outputs. It's all about the opposite of inference. In other words, if inferential problem would be, I give you this coin, I tell you this coin is fair, give me the probability of 3 heads and 7 tails. Can you see that's backwards? That's prediction. Many people think in prediction, they think inference is backwards. How does this fit into the workflow? We're going to take our limited sample data. We sample about 1/1,000,000th of the subsurface directly, volumetrically. Then we're going to make inferences about what the population is. What is the reservoir? Then we can use that to make predictions. For instance, pre-drill prediction. What do we expect at the next well location? That is the inference to prediction workflow. Okay, I hope that helps you. Now we're grounded in value around prediction with our inference, and we can talk more about inferential machine learning. Clustering is a powerful form of inferential machine learning. It goes like this. Many people call it automatic group assignment. I like that. I like descriptive naming. It's very useful. Data segmentation. You improve your prediction models when you do by group stationary set predictions. I don't care if it's geostatistics or machine learning. When you mix a bunch of populations together, you often get a poor result. And we're finding it all over the place, even in machine learning. So it's the same old problems we had in fundamental statistics. We want to also learn the structures from complicated high-dimensional data. I do think there's value to just understanding your data. Okay, so we got a data set, permeability, porosity, and we have a machine, an algorithm that can separate it into clusters or groups. That's what we're doing today. The first method now let me just stop here. If there's any questions or comments, please go ahead and jump in the chat window. When we do regular courses, everybody's off mute, jumping in, everybody's got their laptops open and the running workflows in front of them. For the purpose of a 1-hour workflow, we can't get everybody set up. We can't do all that. So I do apologize. I hate to be non-interactive. So go ahead and jump in anytime. I appreciate it if you do. Prototype method for clustering. It's very simple. We're going to go ahead and represent the data with a set of points in feature space. Now, let me define that. Feature space is when we look at the problem from the standpoint of all the predictor features, porosity, permeability, those two features together, that area is feature space, or more correctly, predictor feature space. Now, prototype is going to be a single value. You see that right there? The star, those are prototypes. They're typically not an actual sample, not for k-means clustering. There's other methods that do use actual samples for prototypes. Training data are going to be assigned to the nearest and usually using Euclidean distance to the prototype. So all of these values are closest to this prototype. All these values, red prototype, red assignment, yellow prototype, yellow assignment. That is the prototype method for clustering. Now, somebody out there is going to be like, I still don't understand how we do that or why we do it or what's going on. Let's get into details. K-means clustering. Show of hands. Who has done K-means clustering before? All right, Michael, I see you. Gamiel, yes. Joseus, yes, I see. Thank you very much for putting your hands up. Now, I'll tell you what, you are my experts here today. You're the varsity team, I guess they say here in the States. So can you please go ahead, jump in if you have insights or ideas. If I missed something important, please help out. It's a community effort today. Okay, let's talk about k-means clustering. What's the general comments, the general structure here? I want to assign groups. Okay, you knew that was going to happen because I said this is automatic group assignment to all data in the feature space, such that the groups are exhaustive. Now I'm being statistical here. The probability of the union of all cluster groups 1 through k groups is equal to 1. In other words, every data point belongs to a group. Nobody gets left out with k-means clustering. That's nice. That makes me happy. Okay, we'll show you a method that doesn't do that, and that's also useful. The groups are mutually exclusive. The probability of an intersection of clusters for any one of the samples is going to be equal to 0. In other words, no samples belong to more than one group at a time. If I want to draw this poorly, I could take my data set, porosity, acoustic impedance, a geophysical property, and I could go ahead and draw a line and say, this is group 1, group 2. But I have to be careful. The line is an abstraction. It's not the model. The model would be color coding all of the points. This clustering approach does not provide us with a boundary or line. It only assigns the data to groups. That would be a predictive model. Can you all see that? If I drew a line and said anything here is now going to be group 2, that's a classification model. That's a predictive model. That's not what this is. It's just assigning the labels at the data locations. Now, every time we do machine learning, we need a loss function. Actually, what's interesting is I teach a full subsurface machine learning course here at the University of Texas. And I'll tell you what, I have to explain optimization, loss functions, because machine learning is based on that. It really is. What we're going to do is we're going to formulate a loss function right here. It's known as inertia, W. Machine learning folks do take a lot of cool terms, epochs, inertia, they do that a lot. We're going to assign groups such that we minimize the inertia. This measure right here is very simple. This double sum is simply going to be the looping over all data within a group, pairwise relative to each other, never comparing a sample with itself. That's what that means. We'll take the square difference. This is a Euclidean distance in feature space, not a big deal. Sum of the squares of all of the differences across all the features. And then we're going to go ahead and we're going to do a sum and a weighting over all of the K clusters. What does this mean? Inertia is a measure of the Euclidean sum of Euclidean distance of the data with themselves within groups. How much are the data dissimilar with each other within the group? Now, this is really important because we'll minimize that. We'll get groups for which the data within the groups are minimally different from each other. That's the idea. Now, if you were listening to that and you're like, oh, the equation, it didn't make sense, let me draw you a picture. I'm going to show you something very simple. Acoustic impedance, porosity, two-dimensional feature space, samples right here. I take my loss function and I minimize such that you see the distances, Euclidean distances between all the sample data in each other is minimized within group 1, minimized within group 2. Now, does everybody see I was a bit lazy? I should have drawn this line going to all other values because we're doing the full pairwise exploration. Okay, now that would be a mess. That'd be a dog's breakfast. I'm not going to draw that. I just drew it abstracted. Now, what's very interesting is that when you minimize this dissimilarity within the groups, you actually maximize the dissimilarity between the groups, which is very useful. That to me makes sense as a good cluster assignment. Okay, we got a loss function. The problem is if you think about it, take all of those data points and randomly switch them between category 1 and 2, and that's just 2 groups. Can we all agree that that gets to be a little bit of a large solution space, right? I think it's going to be number of data to the, or no, number of categories to the number of data power or something like that. It's going to be a big sample space. So how are we going to do it? Well, it turns out we can practically solve the problem with an iterative heuristic approach that I'll show it to you. I'll explain it to you. It should converge to a local minima. There will be a local minima. It could get trapped. There will be a global minimum. Sorry, it may converge to a local minimum. So what we're going to do, practically speaking, is under the hood, we're going to seed a bunch of random starts and take the one that's best. That has been shown to practically solve the problem. So it's not an absolute optimization or ultimate solution, but practically it works very well. Let's explain it. Clustering, we're going to automatically assign all of the data to specific categories. It's unsupervised learning. If you hear that in machine learning, it means everything's X's, there's no Y's. So we have only the predictor features, there's no label provided. It's going to be inferential because we're learning about the system, its structures. It's a prototype method because we use prototypes. It's an iterative solution that I will step through. And this iterative solution is, in fact, a heuristic. Now, what's the definition of heuristic? Part of my job is to teach you terminology that you can use at dinner parties and data science conferences, which are both really cool, right? Heuristic. It sounds really cool. Proceeding by trial and error means you're using a heuristic. It sounds much better than saying trial and error. A method that compromises precision for efficiency and practicality. In other words, what we're about to show you is a heuristic, not a precise solution, but it works pretty well. And a method that it uses an exploratory problem-solving, self-educating approach where it uses feedbacks and adjusts itself to get a good solution. That's a heuristic. I love it. Very cool stuff. We're going to use normalization to do this. Normalization is a procedure that depends on the distances between the samples and the prototypes. If we need to put everything on an equal footing, and I'll show it to you. If we don't do that, we're going to end up with a bias in the system. Normalization is putting all the features on equal footing. Feature weighting could also be augmented here. I will not cover that. And there is a supervised learning classification variant of k-means clustering that I'll comment on at the very end. Okay, so here is my data set right here. Can we start here? Acoustic impedance, porosity. Let's do some automatic segmentation into groups. Now, I don't want to sell this as being so easy a problem. This is a two-dimensional problem. You can see the data. Who here can visualize in 5D, 10D, 16D, 50D? I can't. I can't really go very well above like 5D. It just gets really, 4D is already pretty hard. So we need these methodologies to do what we could not do by hand, for sure. But then that's also objective. If we go ahead and just do it by hand, the subjectivity is pretty high. Now let's think about Euclidean distance. The general equation for Euclidean distance is the square root of the sum of the square differences across all the features. That's general. You can do it in 10 dimensions. Now, in 2 dimensions, it's the delta porosity squared plus the delta acoustic impedance squared. Look at this scale. Acoustic impedance with these units, I apologize, that should be 10 to the third. I don't know why I do that. It should be 10 to the third right there. I apologize to the petrophysicist who may have seen that. 2,000 to 6,000 units. This goes from 0.12 to 0.28 units. What would this look like if I drew it to regular scale without any type of exaggeration? What would this image look like? Could we all agree that that image would become a line on the page, that the X coordinate would be meaningless? In fact, any offset in this direction looks very close. Any offset in this direction looks very far away on equal footing. So we have to do something about that. What would we do? We do normalization. Min-max normalization in machine learning is forcing the minimum and maximum values to be specific values. Min-max normalization is usually 0, 1, or in the case of artificial neural nets, often -1 to 1, based on the type of activation function you're using. So we'll do 0, 1 normalization. 0, 1 normalization. Can you see now that if I take a vector and rotate it with the same length, it would be the same distance now. It would see everything as being the same distance. Okay, we do normalization. Any machine learning method that uses distance calculations in your predictor feature space must be normalized. If you use k-means clustering, please do normalization too. There's a bunch of methods. What we're going to do, the heuristic begins now. We randomly assign k prototypes. Now remember, this is kind of interesting. K-means clustering, you have to inform the K, the number of categories that you want to work with. We pick 3 here, and then we go ahead and seed them in. People see that as a strength. People also see that as a weakness. Gamiel, I do appreciate that comment there. Normalization is a form of feature scaling, agreed. Now, there's also standardization, which is typically setting the mean to 0 and the variance to 1. I would put that all in the broad category of feature engineering, data pre-processing, and so forth. Thank you very much. I do appreciate that comment. Thank you. Comments are welcome anytime. Now we're going to proceed on our heuristic. Now, everything I'm going to show you, I take these initial random prototypes, blue, red, and green, blue, red, and green. And I apologize if anyone has color difficulties with this. Now I'm going to show you in regular space, normalized space. Everybody see that? That's the original units. That's the normalized. You can go back and forth, which is easy. Now, what's very cool is that you can see that the process starting now, we do everything in the normalized space, but we can map everything back because we're just assigning labels to the data. No effort required. We take all of the data and we assign them to the closest prototype. Does everybody see that that happened? In fact, if you drew a line right here, right here, right here, those are perpendicular bisectors in the normalized space. Okay, so these red data are closest to red prototype, blue, green. Now, let me ask you a question. Is that blue prototype a good prototype for this data? Does it look representative? What do you think? Anybody want to vote for awful? That's an awful prototype. It looks really bad. What we're going to do now is we're going to fix it. We're going to take, here's the heuristic. We take the prototype and we shift it to the centroid. I mean, literally take the average of all the feature values for the data set in each coordinate, and you put the data point there. You put the prototype there, and there. We move them, we shift them. How does it look now? Gamila, I agree, awful. I appreciate the vote for awful. Thank you for the interaction. Now, if you look at the data, can you see that this data right here is actually closest to the blue prototype? That's not good. What are we going to do? We update the data assignments. Okay, we do that. Notice what happened. Now these data values belong to that prototype. Now what's the problem? Are the prototypes correct? No, the prototypes are not in the centroid any longer. This one's too far down. Let's go ahead and shift the prototypes and we iterate. Shift the prototype to correct it. Assign the data to the correct prototype. Repeat, repeat, repeat. And if you do that enough times, it will converge. What is convergence? The prototype stops moving around. Okay, this is the final result right here from that process, our heuristic. Will it converge? There is a global minimum that should be found. That's theoretically known. The response surface can be a little rough, the loss function, and so it could get stuck in a local minimum. Not a big deal. We just seed random prototypes, run it a bunch of times, we'll get the best solution. Okay, generally it works well. Okay, so if we take 2 clusters, 7 clusters, this is it right here. Now, anybody watching this and thinking, I've done K nearest clusters, this is kind of, I already know all of this stuff. We're going to start here, then we're going to go to density based. Okay, let me pause here. Any questions, comments? Everybody good? I know we have a little bit of lag here, I'm sure of it. Okay, jump in and I will pause to discuss if there's a question or anything. I appreciate it. Okay. Mr. Rat, I appreciate that. You said good. That's good feedback. That gives me confidence to continue. I appreciate that. Okay, let's go ahead and talk about k-means clustering. Now, I have to confess something. I took this workflow. It's a well-documented workflow, very simple, similar to the one on the LMS system, and I updated it for some students in my class that I teach on campus because they challenged me. They said, we want some cool clustering examples. We want to understand when k-means clustering breaks. I'm a fan of the Mythbusters approach to data science. Run things till they break, run it till the wheels fall off, put a little more pressure, see if it'll blow up. I like that. We learn from that. Adam and Jamie rock. And I heard they're coming back. They're so cool. Okay, so let's go ahead. If you're new to Jupyter Notebooks, they're so powerful. Install Anaconda, get started. It's so much fun. You can create great prototype workflows. You see this is a markdown block. I can run it. I can get documentation, equations, links. I can make very nice workflows. We'll go ahead and run and import some packages. Does everybody feel a little bit smarter? Every time. Oh, you can't see the slides. Let me ask, Paulin, do you actually see the workflow?
Michael, I can see it on my side. Is there somebody having trouble?
Yeah. Do you want to just chat with them and see if they're having a local problem? Avi, I appreciate you jumping and helping with that. Okay, this workflow should be showing, and I'm moving through it, right, Avi?
Yes, it's moving through. Okay.
All right. That's right. Sergey, thank you for reminding me. You see,
is there any possible way to zoom in a tad bit though, Michael? Maybe a little bit.
Oh, you bet. I'm always happy to help. How's that?
Perfect.
Okay, I'm going to give it just one out, just so we can see a little more. Okay, good. Leonardo, thank you very much. We see it. Go ahead. Thanks. That's it. The order's been given. We will proceed. And I appreciate that. That's awesome. Thank you for the interacting with me. All right, good. So what we're going to do is we're going to declare two functions. Now, I want to give full credit to Ben Keen. Anytime I take code from Stack Overflow or somewhere like that, I want to give credit. Here's the link. These functions are from Ben Keen. I liked it. Do it by hand. Let's go ahead and run those functions. Assign the centroids, update the assignments of data to the nearest centroid. That's all we're going to do, okay? This corrects the centroids, sorry, the prototypes, and this reassigns the data to the nearest prototype. So I got that switched up. Sorry about that. Let's go ahead and load a data set. We're going to start with, we're going to have 3 data sets. We'll do this pretty quickly just to see where it works, where it doesn't work. Data set number 1 was built for k-means clustering. We'll go ahead and load that up. My students said we want an easy one to get started. So I made an easy one to get started. See if you agree with me. Let's go ahead and we're going to take a look at the data set. This block right here is where we set the number of clusters. You know what I'm going to do? I'm going to set that as 3 clusters. Just let's take a look at the data set and then see if you agree with me. 1, 2, 3, 4, 5, maybe 5 clusters. 1, 2, 3, 4, 5, 6, maybe 6. Let's just try 3 to get started. This is a normalized space. This is where the math is getting done, just so everyone understands. Now, what's very interesting is that this should work pretty well with k-means clustering. Let's try it out. We're going to assign centroids. 1, 2, 3. Everybody see my 3 random centroids? What's the first step? You remember? Assign the data to the nearest centroid. Okay, let's do that. Data to the nearest centroid. Now we're going to shift the centroids. So we're going to go ahead and shift our centroids. Then we're going to run. We're going to iterate until we converge. And when we do that, this is the solution we get at the very end. Okay, who likes my clusters? Who thinks I did a great job? Is it going to be turkey for Christmas? Am I getting a bonus this year? Paulin, Mohammed, Leonardo, Sergey, how am I doing? Great? No, we could improve it. Would you all agree we need to change the number of great? I do appreciate that encouragement. I do feel validated now. Oh, Leonardo, you asked the magic question. How do you know the number of clusters you should use? This is the dilemma and the power of k-means clustering. It is the hyperparameter. It's the input to the model. Now, Sergey, I do agree. People do look at how they can change inertia, drop inertia, but we got to be careful with that. Because imagine what would happen if I seed in imagine a very large number of clusters or prototypes. At some point, you're going to reach a point where you can get to 0 inertia. Okay, so I'm a little bit careful about just setting it based on what inertia does. I do side on the side of using more expert knowledge. Okay, I would agree. Let's try increasing the number of clusters. I do appreciate the feedback. Let's go to 5. Now, I'm going to confess something. My code, yes, Masha, exactly. And thank you very much. Nice to hear from you. The number of prototypes is going to be the number of resulting clusters. Now, there's a weakness in my code, and that is, let me show it to you. If the original prototype gets no data assigned, it'll just disappear. Now, under the hood in scikit-learn, it'll do a correction. It'll move the prototype to ensure none of them get accidentally dropped. Okay, 1, 2, 3, 4, 5, random initial prototypes. We assign the data to the nearest prototype. Okay, let's go ahead and do that. 1, 2, 3, 4, 5. Look at that. These are our prototype assignments. Now we can go ahead and update the prototypes, the data assigned to the prototypes. We can update the prototypes. We do that right there. And we can iterate over and over again until we converge. 1, 2, 3, 4. That's actually a really good solution. Now, did you see what happened? We dropped one of the prototypes because it failed to get a data point assigned to it originally, and it dropped. It was the one down here. But this actually looks pretty good. Would you agree? Not bad. Okay. Now, I had students who said, can you show me an example where this doesn't work very well? So we're going to jump ahead. Looks okay. Thank you very much for the feedback. I do appreciate that. Let's go right up to the front. Where is it? Sorry about all the movement. I hope this isn't irritating. K. Oh, let's go back to picking the data set. Let's pick a more difficult data set. Mohammed, thank you very much. I appreciate that. Let's pick data set number 3. Let's take a look at it before we say anything about the number. I shouldn't assign the number first. I should have looked at it. This is my data set. It's acoustic impedance versus porosity this time. How do you like my data set? Is it going to work well? When you see, how many groups do you see? How many groups do you see when you look at this data set? It'll break. I see 3. Mohammed, I see 3. Masha, if you want to see 4, you're a bit of a splitter, and I can understand why you see that. Maybe you're looking here. Okay, 3. You know why? Because your brain is thinking about density. You're thinking about density. Okay, will k-means clustering work? What do you think? Somebody said it's going to break. Let's show a break. Wow, look at this feedback. I appreciate that. Okay, here we go. 1, 2, 3, 4, 5. I'll tell you what, everybody said they saw 3. Let me go back here. If you'll let me have a do-over, I'm going to switch it to 3 because I want to listen. I'm democratic. I'll listen to the voice of the people. So say we all from Battlestar Galactica, right? So let's go ahead. And that's my 3 initial prototypes, my initial assignments. Let's go ahead and update my prototypes. It's looking pretty good. It's getting better, right? I run it a bunch of times, iterate until I converge. What do I get? How do you like my clusters now? Is it turkey for Christmas? Am I getting a bonus this year? Will my boss be so pleased? Poor. Yes, not at all. No turkey for Christmas. This is a poor result. This is an example of k-means clustering breaking. It needs to be modified. Yes, Mohammed, I agree. Okay, so let's go ahead and let's talk about why it broke. Okay, everybody ready? The fundamental assumptions of k-means clustering are very important. Spherical, convex, isotropic clusters. Okay, spherical. Why do we say spherical? Because it could be multidimensional. They should be circular. You know, Sergey, features are not independent. I love it. I love it. When you think about spherical structures in multidimensional predictor feature space, I think of zero correlation. If you have a high degree of correlation, you create elongation. That will break this assumption of spherical. Yes, equal variance for all features. Now, we took care of that with our normalization, min-max normalization. Thank you for the feedback on that. We're good. Similar size and frequency clusters. I'm not going to get into those details. Let's just explain convexity. Why do I explain it? Because it's cool. And remember, part of my job is to give you terminology you can use at data science conferences and dinner parties. Okay, and I use these terms at dinner parties with great success. Kidding. Okay, here's an example. I have a data set. I've drawn an envelope around it. Thank you for the haha, appreciate that. I draw an envelope around it. Okay, now I take any 2 random points. That envelope is an abstraction. I'm just basically putting a boundary around my data set in 2 dimensions. I take any 2 random points. I draw a line connecting them. The line that connects them exists within the envelope. That's convexity. Here's an example right here. The data set, I draw my envelope. I take any 2 random points. The line is exceeding. It's escaping the envelope. That's non-convexity. Does everybody understand what a convex data set is now? This can happen in 10 dimensions. Gets complicated. Okay, let's take a look at a data set very similar to the one I just showed you, different but similar problems. Is this convex? Is this spherical? Is this equal frequency? Does this look great when you do k-means clustering? This is k-means clustering. Do you see how it breaks? It looks awful. Your eye knows these clusters. K-means clustering cannot see them. What are we going to do? We're going to use density-based clustering. Let's do this. This is kind of fun. The method we're going to explain now is density-based spatial clustering of applications with noise. Have you ever made an acronym where you had to try too hard? DBScan looks like they tried a little too hard, but I'm giving them full credit. It's a great method. It really is a powerful method. It's hierarchical from bottom up. It's agglomerative. Another word you can use at a dinner party, clustering. All sample data start as their own group by themselves, and then you group them together. You grow the groups organically. Mutually exclusive, all samples may belong to only one cluster. That's k-means clustering, the same idea, but non-exhaustive. Remember how we were exhaustive with k-means clustering? You can, in fact, belong to no group. You can be an outlier, which people think is really cool. Okay, density-based. This is something important. If I talk to you about data density, you're looking again at a map of data points. What does density mean? It means that over a certain scale, you have a high number of points. You see that? There's 2 concepts to density. What's the scale? What's the area? What's the size of the circle you're looking at? What's the number of data to be dense? Okay, we need those two measures, the radius, the scale, and the minimum number of data to be considered sufficient density to be a group or part of a group. Once you have those two hyperparameters, you're doing dB scan. You're ready to go. How do you get them? Well, the actual scale parameter usually comes by doing a k-distance graph. K-distance graph comes directly from spatial point data analytics, okay? And so what we're gonna do is we're gonna run this k-distance graph, which is just simply gonna look for the lag one, the closest data to any data point in Euclidean distance in the feature space, and that's gonna sort that. If you have 1,700 data, you'll have 1,700 values to the nearest data point, and you'll look for the elbow. Now, the elbow can be subjective. It can look multi-scale, it can be complicated, but something like around here could be suggested to be a reasonable elbow. That's commonly used to detect the scale that you should be working with. Now, in this route, you asked the question, what if you have two dramatically different distributions? dB scan uses a distance measure also. Now, this is very important. It means that we should normalize to ensure we're on equal footing, or we will create a bias, a weighting unintended. Just think about it. If I change the porosity values from percentage to fraction, I change variance by 10,000. Like dispersion changes dramatically, distances change dramatically. Let's normalize again, okay? What if you have 50 dimensions? Leonardo, you took us to 50D. This is awesome. I watched 2010 Space Odyssey last night. I'm ready to answer this question, okay? 50 dimensions. First of all, I start to get concerned about the curse of dimensionality and whether distances mean anything in 50 dimensions. So let's just be careful on that. The methodology to assess convexity, whether things are spherical. My suggestion would be this. What is going to be spherical in 50D? Probably only a Gaussian 50-dimensional mixture model. Everything else is probably going to be non-spherical, non-convex. I'm just saying that in general, we'll probably have to assume in high-dimensional spaces with real data, non-convexity, non-spherical. Only very idealized, simple examples are, hence why we do dB scan. Let us do dB scan together. I created an animated slide set. This is a multimedia extravaganza. I hope this is helpful to you. What we do is we take all our data, predictor feature 1 normalized, predictor feature number 2 normalized. We're going to assign epsilon, the radius, the scale, and the minimum number of samples to say dense. It's dense. We're going to randomly visit a location. We go here. We put the circle down. We look around ourselves and we see how many data do I have around me. Now, this, of course, can be in whatever dimensions, circle, sphere, so forth, hypersphere. We look around ourselves, we don't have 4 samples, that becomes an outlier. Boom, we're done, we're done. Now we go to a random location, we put a circle down, 1, 2, 3, we count the data point at the middle, 1, 2, 3, 4, 5. Oh, that's enough, that's sufficiently dense, that becomes core. Okay, good, good. Now we got work to do. This is agglomerative, we're gonna grow. So let's start growing. We're gonna go to all the data within the circle, we're gonna check them. This doesn't have enough data, it becomes boundary. We're done. This has enough data, this has enough data, they all have enough data, they're sufficiently dense, they become new core points. We got to go back to work again. We're going to go visit all of the core points and repeat the process. You see what we're doing? It's a recursive algorithm. We're going to keep going, growing. We'll assign boundary points, we're done. We assign new core points, we keep going, and eventually the fire is going to burn out. Okay, and we're done. At that point, there's nobody else with sufficient density to continue. No new core points. We're done. Okay, I hope that was useful. Now we go to another random location. Oh, outlier. Another random. Ooh, 4. We got a new core point. Now we're going to start doing agglomerative growing. Okay, another core point. Got to keep going. Another core point. Got to keep going. Boundary point. We're done. Okay, now we visit. And we go randomly around, we found a bunch of outlier points and we're done. We got assignment of core, boundary, and outlier. Questions, comments, go ahead, jump in. Now we introduce a couple of concepts that'll get us there. First of all, directly density reachable means Game of, like, you know what's very interesting? If you get me talking, Masha, about the kind of philosophy of agglomerative growing and clustering and what it means in life and so forth, yeah, I like it. It kind of reminds me of ripples in a pond and how we influence each other and so forth. It's a beautiful thought indeed. Very cool. Thank you for that. Directly density reachable means that we go from a core point to any one of the points within epsilon. That's directly density reachable. Now, density reachable, if we can do that through directly density reachable core points chained up, and then we go within its last region, this point is now density reachable from that point. Do you see what's happening? We're growing chains. Okay, now we have one more concept. It's called density connected. If we have directly density reachable, and then we have if we have an example where we're directly density reachable from here to this boundary point, and then directly density reachable to this boundary point, and they're a common boundary point, we now chain the whole thing up and we call that density connected. Okay. There's almost like a Kevin Bacon thing in here with degrees of separation. But once we've done that, we'll say that's a density connected set of points. Okay, density connected set of points, cluster one, density connected set of points here. So we now have groups and we have outliers that remain as outliers. That, my friends, is dbScan. Okay, are you ready? Can I show you an example of dbScan? I think this is a lot of fun. So let's go ahead. We're going to import some packages. I kind of jumped through this before. How's the font? Can people see the font? Are you guys okay with my font on my workflow? Okay. We're going to load up from scikit-learn the cluster module, the scikit-learn package, cluster module. Thank you, Mohammed. I appreciate that. We're going to import dbScan. K means clustering too. So easy to import and work with the world of brilliance. Thank you so much, scikit-learn and open development. We love it. It's so powerful. Let's go ahead and load up a data set. I'm going to give you a simple data set to start with. In the class, we would walk through it, and then I would hand you another data set and say, okay, you figure this out. You try to figure out what to do. Let's take a look at the data set. First of all, I do know the truth. You don't use the truth because this is unsupervised, but I know the truth basis classifications, and look at that. It's not uniform frequency. That invalidates k-means clustering already. So we know we're going to have a problem. But guess what? We're going to do the normalization. Now we're going to finally get around to visualizing this. This is my data right here. Okay, now once again, the color coding is not known by the machine. That's the truth model. Really what we feed the machine is just all of these points, and we have it try to figure it out. Can everybody see? Non-convex, complicated, but your eye can see density connections. So the machine should be able to see it too. Let's go ahead and let's try k-means clustering. Why do we do that? It's not a bad idea to just try running it so we can kind of see how bad it is. If anybody's interested, here's the code right here to do k-means clustering. One line of code to set the hyperparameters right there, the number of clusters, prototypes, the random states, so you can control the whole heuristic iterative method, and we all get the same answer. And you can fit it with the data right here. Boom, you assign labels and you're good to go. Okay, and then we get this result right here. So easy to kind of get some of these methods going and experimenting with them. So much fun. Now let's go ahead and look at what would happen if you didn't do normalization. This is a plot without vertical exaggeration, permeability, millidarcies versus, that's not porosity. Geez, that's supposed to be acoustic impedance or something. That's weird. Okay, I'll fix that in the future. Sorry about that. I got the wrong label. Now we'll go ahead and we'll do clustering. We'll do clustering on that. If we do clustering without min-max normalization, does anybody see the horizontal line right here? Horizontal line right there? If you do it without min-max normalization, porosity is meaningless. It has no impact. It becomes a one-dimensional clustering problem, and you can see it expressed as these horizontal lines in the clusters. If we go back to this, can you see the line is like that? It doesn't have that horizontal behavior. Okay, I want to give you an example of doing badly. Let's go ahead and look at dbScan. Okay, dbScan. We're going to instantiate dbScan. We already imported it with epsilon minimum number of samples, 10.025. That's in Euclidean distance in the predictor feature space. The rest of this is plotting. That's it. Here we go. This right here is my dbScan result. Category 3, category, where do we have here? We got a blue category somewhere. We got a yellow category, an orange category. That's the result. We can do better. Let's go ahead. Let's do some trial and error, our own heuristic. Let's set the epsilon and the minimum number of samples to make a cluster as these numbers right here. And let's run all of these results. If you look at it, it's kind of fun. You can actually explore and see how the parameters do, the hyperparameters do as far as getting good clusters. I don't think we've really tuned into it yet. Let's go ahead and try using the K nearest neighbor plot. We do that. We got the same thing as this course notes. We can infer from it a reasonable epsilon value. We pick 0.025. We rerun it. Now we take a look at this. This is pretty good. We got this group, this group, this group. Now it did break it up to these two groups over here, this group right here over here. We could consider joining some of these groups. Okay, I'm going to stop right there as far as dbScan goes. Granted, I gave us a difficult problem to work with in the lecture notes and the workflow on the server, on the LMS. You have the ability to come back here and try out for yourself a brand new example. You set the experiential learning on true, and you go run it and you'll get this different data set right here. Let me see. Let's take just a quick look at what the data set looks like. This one's a different example. I think you might find you have a different degree of success here as far as segmenting using density-based clustering. Okay, let me just make a couple of comments and finish up. I do, once again, when we do like full courses together, you work with the workflows in front of you, we work in teams, we break things up, we explore, answer questions. In this case, we're just kind of quickly, me just kind of touching the keys and showing you things. So I do apologize for that. We don't have time to do everything within a webinar like this. I'll tell you what though, Avi, do you have any comments or anything? I want to see my speaker turned off.
No, Michael, I'm good. This was great. Definitely good overview for clustering and everything. As you said, if folks are interested in seeing more, actually want to get hands-on keys, I think that's key as well, right? So we could see sample data. I know you teach the full course as well, so this is great.
Awesome. Leonardo, I do appreciate you sending your question in both the Q&A and chat window. I apologize, I didn't see the Q&A, but you did ask in the chat window. I'll hang out here. I actually have a little bit of time, so if anybody has any questions, I can hang out here and discuss.
I have to jump, Michael. I'm going to go to another meeting. You're a co-host, though, so you'll be on if you want to answer any questions.
Yeah, I'm not going to disappear.
You won't disappear. We have you.
Hey, Avi, thanks for all your help today. Very awesome.
You got it.
So stay safe. Anybody by chat window, any questions? I welcome them. Thank you very much for everyone joining in. I do appreciate it. Really nice to see everyone. Hot here in Texas, 100 degrees the last day or so. I hope where you're at, it's not 100 degrees. Oh, okay. So a couple of questions coming in here. Can we have some comments about Gaussian mixture models in clustering? And I do appreciate that. The great thing about Gaussian mixture models is that they do have a non-convexity aspect to them, but as already raised by Nusrat, the idea that they're not independent of each other will create non-spherical type of behavior in the predictor feature space, which can really make it problematic. The other thing that I find very interesting, if you make, and I've done this recently for fun, make yourself a high dimensional Gaussian mixture model. What you'll find is that the overlap between multiple Gaussian, multi-Gaussian distributions will actually create nonlinearity. And it'll create kind of what appears to be more complicated structure, which can make it very challenging. Okay. Now, Masha asks a really good question about text classification. And it's a very good question, you know, on the idea of, can we use dbScan to try to figure out what's going on with text? The issue with text is the fact that it becomes more of an image problem. And when it comes to image problems, people have found recently that methodologies that actually account for the locality, the structure from point to point within the image can be more powerful. And that's what's driven us really to go, PCA used to be a big part of that too, to go towards convolutional neural nets. Now I do have lectures and examples on convolutional neural nets, if that's helpful to you. Actually, 2 weeks ago for fun, I built a bunch of simple examples in CNNs and just tried things like detecting randomly located artifacts within images. It's really fun to run. You're welcome to try these out. Okay, and Mohammed, thank you very much for the appreciation. I do appreciate that. Christopher, you got a server error 500 when registering. Thank you. We'll let Avi know about that. I think we heard about someone else. Christopher, just let me know. I'm going to guess it worked at the end. Okay. Masha, thank you very much. I do appreciate the appreciation on that. And thank you for the interactions on Twitter. Nice to meet you. And thank you for attending. Any other questions? Oh, what is the, Nasrat asked, what's the question? What's the recommended method for permeability prediction? Let me make a couple of comments about permeability. Geez. The first comment I'll make is because I'm a geostatistician, we ignore the scale of permeability in many of our models. And that can be very problematic when we're trying to make predictions. Leonardo, please check out on Datum. You can register for free and then you can see the LMS. Anyone can participate and check out all the LMS files, the lectures, the record. It's all shown. Avi was showing an example at the beginning. I hope that helps you. So when we talk about permeability, we have that issue as far as the scale. And I just want to throw that out there, almost a wrench in your cogs to realize that there's a lot of issues with permeability. The other thing that permeability tends to not average linearly. And many of our prediction methods still kind of rely on a linearity assumption. So I want to kind of challenge things there. Now, a natural tendency with permeability is to do log of permeability. Now, I'm trying to remember who it was. Was it Matt Hall or someone like that did a rant, a blog post about the issues of using log transforms on permeability. And that's been shown, of course, as a known statistical issue of causing bias. It has to do with the assumption of linear regression. I get to say it again, homoscedasticity. The variance does not vary over the magnitude of the values. In other words, that error component is constant and uncorrelated. When you do the log transform, you invalidate that, and that tends to cause a bias. And so we got to be very careful. I'm not saying don't do it. I would say take a look at the results. What people often do is they fit a model in log permeability space and they forget to go back to original permeability space. You'll see it. You'll see the bias. It'll look really pretty obvious. And you can check for it using conditional statistics. All right. I've hung out here for a little bit of time. Oh, Nusrat. Oh, the blog post by Matt Hall. Oh, geez. I'll tell you what. Send me an email. I'm easy to find. And I can take a little look around because, you know, I'm having kind of a realization here. I believe it was a professor from Germany that I know on Twitter. I can look it up. They had a blog post on it. Okay, Matt Hall, I apologize. I gave you, I unfairly accused you of or gave you false credit for an article. But, you know, it seems like the type of thing Matt Hall would talk about. Okay, send me an email. Okay. Awesome. Okay, I'm gonna bail right now. I better get to my next things, but I do appreciate it. Thank you very much for everybody who joined in today. Please stay safe. I appreciate it, and we'll see you out there. Okay, bye.